We'll get started here for this October the 19th, right here in the middle of the semester. Maybe all the cold has got everybody frozen in their desks or seats or something like that here for today. But thanks for everybody joining and otherwise watching online later. Today we have Robert Engebretson with the development of passive and repeatable tape spring deployers at Virginia Tech. This is another one in our series of UpRosat seminars that I think we'll have at least one or maybe two more here in the semester, if not into next semester. Without further ado, I'll turn it over.
Okay, this is a overview of the history of Virginia Tech deployers, deployers at Virginia Tech and how it led to ProSat. Now, deployers launch tape springs, and tape springs are just straight rigid bodies that can be forced out of its default shape into another more compact one, but once released, they will return to their original state. Now, some of these tape springs can be coiled up, sort of like into a spool, which allows them to be a very compact cylinder shape, but then released into a long sort of boom that could be used for various things. But in order to do that properly, you need a device, which we call a deployer, that constrains deployment so it doesn't just go everywhere, it goes into one specific direction. And there's been a series of projects at Virginia Tech that has accumulated into deployer design that we're going to fly into ProSat. Now, here's what an unconstrained deployment of a tape spring looks like. It's a bit glitchy.
Yeah, maybe kind of sense.
Yeah. Now, the first deployer that at least I was working on was designed as an undergraduate project to study the deployment of tape springs. It was going to use several different tape springs to determine how their physical properties affected the deployment. And specifically, we want to determine a cone of uncertainty in the flight path so that we could determine if it was safe to launch them close to another satellite object, making sure it wouldn't hit it. The deployer we made had to accommodate different sizes of tape springs reliably at the same time in order to get the reliable data. So what we came up with as an undergrad was the first version. It was two panels held together by clamps, and then 7 rigid wires were suspended. The rod positions could be changed depending on the size of the spool we were using at that time. And we had just simple beads that were able to roll and reduce the friction on the deployment. And with this setup, we used OptiTrack to measure the position of the tip of the boom 240 times per second. Okay. That was a really fast deployment, about 5 feet. And you notice they're just general off-the-shelf tape measures, which are basically just tape springs. They just have an internal torsion spring to make them do the opposite most of the time. And for this deployer was very reliable. It was able to perform 50 deployments of each of the 5 different tape springs. And despite breaking in the middle, we were able to get repairs, but 250 deployments is not bad at all. And with this data, we were able to do cones of uncertainty for each tape spring, which would allow us to determine the probability of collision with another object. You see this here, made in Mathematica. Now, this went on to ThickSat. ThickSat was a mission I was put on that sought to demonstrate a passive deployer in space. It's called ThickSat because it was made up of 6 thin sats and ended up being approximately the size of a 1U CubeSat. The satellite didn't have a lot of room for a deployer, so we had to make a much more compact design developed for just one specific tape spring now. This new tape spring was provided by NASA, and it was much more sophisticated, made of carbon fiber, layered with epoxy. And this material was much better for a space environment than whatever tape measures are made of. This cross section known is sort of a collapsible. It's known as the double omega shape and allows the beam to be very rigid, sort of like stretched omegas that are mirrored and attached at the tips. The prototype we did, which I heavily based on design from the OptiTrack deployer, because we were able to place the rods and beads with ball bearings since we only had one size to deal with. It was all designed to fit in a 80 millimeter cube area, and initial testing showed that only the 4 of the rollers were necessary instead of all 8 here, so that helped further compact the design. What we needed for this to operate autonomously, which is brand new, we needed a sort of trigger that could operate by itself. The first method we tried was using a burn wire that was interlinked with a fishing wire that could hold back a cover on the tip of the tape spring. We had to use a large capacitor to vaporize the burn wire, but ultimately was not too feasible, as the now free fishing wire would often get stuck along the axle of the spool and jam it. And also the capacitor was very large. I think it was like almost an inch in diameter, if I recall. The more reliable method, which would see future use, was attaching an arm to a servo that would fit into one of many slots onto one side of the spool. When it was time to deploy, the servo would rotate the arm out of the spool, allowing it to deploy. And this was a very secure design, as the rotation of the servo was perpendicular to the rotation of the spool. So the only way it could actually release under pressure from the spool was if the spool was strong enough to actually break it, and that was nowhere close to ever happening. And this would be a staple in future designs. The first successful deployment of this version then fell off, but it worked well. Yeah, and we made some additional improvements for the final design. One of the corner rollers was replaced by 2 guiding rollers in the front to help direct the direction of deployment. We had a sort of insert on the spool to put the base of the tape spring in, so it would be more secure. Made room for an attachment for a camera that would help confirm the deployment. And then we cut lots of holes into the side panels to save on mass. And we had the structure, which was just 2 overlapping panels with screws, which just replaced something more sophisticated. And a cover on the tip of the boom was needed to keep the tape spring from retreating all the way back into the deployer and to keep it taut, because while the servo kept the spool from rotating, the boom still wanted to attempt to straighten, and that would cause it to expand, and that would pull back on the tip. So that had to be vented and also kept relatively tight with one another, so it would still be elastic enough to deploy. We learned many insights in these types of tape springs. One is that when we tested under cold temperatures, it didn't deploy as readily once it got below freezing. It appears that tape springs of this material use a lot of elasticity when exposed to cold temperatures. And this one in particular, likely due to its particular shape, the repeated deployments caused damage to the tape spring in the form of cracks. And eventually that meant the tape spring no longer worked as well as a tape spring, and the deployer would stop working. Each boom could only survive about approximately 100 deployments. So now this all leads to UPROSAT-1. It's an upcoming mission for 3U CubeSat mission. It has 3 payloads. The primary one, which is the boom deployer. The mission will last not 10, not 5, but about 2 days now, depending on exact orbital configurations. The objective of the mission is to evaluate the reliability of the deploy by testing the deployment multiple times. Multiple deployments also identify variables that affect whether the deployer succeeds, such as temperature. Additional objectives include capturing acceleration data with an IMU at the tip of the boom. And the results from this mission will allow us to have some insight into how viable this type of deploy would be for future deployable structures, such as on solar sails. And one of the key features that will have to be integrated into this deployer is a crutch mechanism so that the passive deployment is not disturbed by the presence of a motor that will be required for the retraction. For this mission, we had a new boom, which was considered bistable. It had the same material composition as the previous thick-sat boom, but was larger and had a different shape, which is now parabolic. The main feature of this boom is that it was considered bistable. So while it acted similarly to the old boom, it had a straight configuration it preferred. Unlike the other, once you flattened and coiled it, it would actually stay in that coiled position unless slightly perturbed out of it, in which case it will return to the original straight one. And you see the two different configurations here. The first step was to characterize this bistability, and we used an initial deployer heavily based on the thick-sat one just to get a general feel of it. But it was designed so that we could try multiple sizes of spool to see which one fit. We had a 50, 70, and 90 millimeter diameter, with 90 matching the bistability diameter. We found that having the smaller spools made it act more like the thick-sat deployer, but we felt that the 90 millimeter spool was better, as since it was bistable, it didn't actually need the rollers to constrain it, it just needed guiding rollers. And this would also demonstrate the bistability, which NASA was very interested in, so we decided to go with the 90 millimeter diameter. Now, the first thing we need to do is a crutch. The first serious consideration was using two face gears that, once they were connected, would allow motion to be transferred from the spool, which one face gear was connected to, and to the motor, which the other face gear was connected to right here. The first design had two solenoids for balance on either side that would push a ball bearing holder forward. The face gear here would interact with this one through a ball bearing. It had a insert that would go inside the ball bearing, and the ball bearings outside was attached to this, so that both of these would move together linearly, but could rotate independently. So the face gear could rotate with the motor that was driving it, but this would stay static in line with the solenoids. The motor shaft was able to pass through the ball bearing directly into the face gear to allow this. But the solenoids did not seem to work quite as well, and due to constraints on the electrical design, we decided to go with a servo no matter what crutch design we used. So the first attempt to utilize the servo would have two arms with gears attached to a modified holder, and these gear teeth would fit into gear teeth on the new holder, and by rotating the servo, it would transform the rotational motion into linear motion with the face gear. But there were difficulties with this design. The effectively had a really high gear ratio, so a lot of torque would be lost in pushing it, so it wouldn't have proved quite as useful. The first successful design modified the holder so that it is now a gear, and it's driven by a servo gear. So, and with the threads on the inside matching threads here on the frame, when this servo gear rotated, it unscrewed this gear, which pushed it forward and causing the face gears to mesh. And then it could also do the same thing, pushing it backwards. Now, this actually increased the overall torque because it was very efficient transfer of rotational to linear energy. So we went forward and made a prototype of this design. It performed very well. The face gears were able to properly clamp and re-spool the deployer, as well as allowing it to deploy easily afterwards. The threads, one noticed that the threads had to match precisely, or else the holder gear would torque slightly and jam the entire thing. Even when the face gears did not properly mesh, like if they just came in contact teeth to teeth, the pressure between them was still enough to keep them rotating and allow motion to be transferred. While it was effective, the on-screwing clutch took up a significant volume, which was limited on the 3U area, 3U volume. Ideally, the mechanism would be placed inside the large available volume of the spool. And there was one derivation of this that involved moving the mechanism inside the spool, but it required a very large ball bearing, which would have been somewhat expensive and a bit infeasible for re-entry, as it would have large metallic parts that would be very likely to reach the surface. So a new design using what's called the aperture clutch allowed the motor to be placed inside the spool in order to save space, and had a compact clutch mechanism embedded into one of the side panels. The body of the motor in this design is directly attached to the spool so that it rotates if the motor activates while the shaft is fixed, and it will freely rotate just together if the shaft is not fixed. And we have a demonstration at the bottom of it able to switch between the motorized retraction and the deployment. And here's a small visualization of the mechanism, which I shall describe in more detail. Next slide, you see the deployment again. Yep. Now for the aperture clutch, this works using a servo, and this servo, like the other one, drives a servo gear, which drives this ring, causes it to rotate a short distance. Now these three tabs have one peg that's attached to one place on the ring, and they have another peg attached to this groove. Now and then on the other side, they have another groove that's attached to this one. And these grooves are identical except they're mirrored. And they intersect at one place that changes as the ring rotates. So as the ring rotates, this part of the tab is forced inward, surrounding this 3-star spoke, and wraps around it in the gaps between the spokes. This allows it to clamp onto the star, and this star is directly attached to the shaft. So once they're clamped on together, the shaft is held fixed, and running the motor will instead drive the body of the motor instead of the shaft and drive the spool forward. But once released, this shaft and the motor and the spool with it is now free rotating, and the deployer can now deploy under its own elastic energy. Here's a demonstration of the working. Here's our deployment, and you can see the two grooves sort of changing their intersection point. Let's do that again. The deployment, tabs move inward, and now it can retract safely. Now into development, we had a new boom, which was slightly smaller as requested, because we were concerned that the boom we were using was a bit too large and a bit too close to comfort for our 3U CubeSat. So the new boom was smaller, the smaller cross section and coil diameter, but it came with double the length at 4 feet. And we were expecting this one getting, but this one finally came embedded with electrical leads that allow power and data to be transmitted across the boom. This is how we're going to collect data from the IMU on the tip of the boom. And we made significant adjustments to the deployer. The bridges that connected the two deployers were adjusted so that they could allow wires to pass through, allowing the mechanism on the right side to be connected with the electronics, which were going to be on the left side. Diameter spool was shrunk around the middle to accommodate the smaller tape spring, but the overall mechanism was not shrunk for this in order to maintain easy compatibility. And the servo locking method from ThickSat was used as an additional fail-safe that would be in place before orbit, and it would trigger the first deployment of this, with the subsequent ones being used by the clutch. Is a deployment of the close to final one, where we don't have retraction here. One important piece is the tip attachment. We like the thick set, we don't want the boom to go all the way in. So we have, we have a flexible cover that attaches onto two guiding rods. They're straight and they only attach at the relatively straight parts of the parabola, so not to interfere as much. Like I said, if this thing were to fail and the spool would go all the way in, there would be no way to uncoil it in orbit. The cover also has hooks on top to catch one of the guiding rods up there, so that it's a nice and secure connection for the final deployment, and very useful for the science team determining how the boom is reacting under the IMU. And a torsional spring helps force a transition from flat to parabolic, just helping torque it a bit more so that deployment is a bit more energetic. Additionally, in order to transfer the data from the rotating spool to the non-rotating rest of the spacecraft, we needed a slip ring, and we made an in-house one since there was not an easily available vacuum compatible one, especially of the size we needed. And this is why our design with the spinning motor works so well. For the IMU, we were going to need a slip ring anyway. So having the motor spin with the spool and be inside the spool wasn't a big deal. All we had to do was increase the number of leads that the slip ring would accommodate instead of just adding this new entire thing. Now, the slip ring is just a simple one. The wires from the electronics are soldered inside of the rings, and the wires from the spool are pressed against the surface of the rings using a torsion spring, but they're not actually attached, so they can slide across the surface. And some basic instrumentation. There was a visible light camera that's going to take the image of the boom once fully deployed for confirmation on the ground. An infrared camera that we record the temperature with, and we can determine how much of a variable that was. And it will be able to get an entire profile as the boom is retracting and deploying. An encoder keeps track of the angular position of the spool, and that's important because that's the only way the spool can determine its location autonomously. An inertia measurement unit we've mentioned before that take acceleration from the tip of the boom. We had some initial testing with the TVAC. This allowed us to determine how well it performed under hot and cold condition while under a vacuum. And the boom didn't do as well under cold conditions, which is similar to what we saw during thickset, where the boom was less elastic when cold. And however, this is the first time we tested it with hot conditions, actually performed better than at room temperature. So there seems to be an overall correlation between the elasticity and the temperature. The actual operations of this mission, the minimum success criteria is a single deployment to match what thickset mission would have been. Thickset didn't work, by the way. Initial deployment will be confirmed by the ground before any retraction is attempted. And the additional deployments will continue in the same manner while collecting that data over time. And if the deployer is reliable enough, it may be instructed to operate autonomously in between passes to allow even more deployments to be made between each pass. Thank you.
I did see a couple of people joined online here, so any questions here for our speaker today? Why they're thinking of stuff.
So Rob, great presentation. I really enjoyed it. I think you did a well-deserved storyline between where you came from, big set, percent, the evolution of the design, that culminated in this optimized design for employer. That is fantastic. Presentation. My question is, I've heard you're doing a balloon flight with, and then you're trying to deploy this on high altitude here in the atmosphere. Like, what do you think you're expecting to see in the environment conditions on this flight? Somewhat related to what you it was hinted to you in terms of like temperature and elasticity.
Yeah, I've been wanting to do the balloon flight mostly just to get a sort of experience. It's like an autonomous sort of flight, so the entire electronics and deployer have to work by themselves. I think that's the most important part. I haven't been too confident that there'll actually be a significant deployment because of that cold temperature limitation, but I still think it's valuable regardless. And for I know, it could be different. Like the direct sunlight on the boom might keep it a lot warmer than we might expect at that temperature. I personally don't have a whole lot of experience with the temperatures up there. I know the air is cold, but I don't know how what it transfers to the actual balloon spacecraft.
I'll jump in for anybody that's online. So you mentioned earlier about doing like the 250 deployments, and it goes more on the TICSAT design, and how you ended up kind of shredding some of the carbon fiber parts. Is that you kind of looked at that as part of with SmallSat in doing that, like when it goes to like autonomous mode, you know, how many times you might expect it? Do you have that kind of resource available where you can kind of basically wear one out, or again, that's not your flight one?
Well, we are much more limited on the number of booms we have for this one, but we don't think braking is as much a concern as with this one. As this one had a very awkward shape, it would have been this omega shape, it would have been flattened and then curved. Meanwhile, this thing is a lot more like a normal tape measure type tape spring. So I don't think it doesn't have as much internal stress being placed on it when it's being compacted. And we didn't notice any deterioration under normal use. Mind you, there was one boom that was destroyed under some abnormal use, I would call it, but not during regular deployments. And even if it was on par with the 100 deployments of TICSAT, I don't think we're going to be able to get 100 deployments in orbit. So,
Yeah, you say only 2 days. That's
yeah.
Just for 2 days. Yeah, my other question was going to be about that. You know, what do you think is causing that issue with the thread? And do you think it's mostly just that, you know, flattening down and then happens to expand? And that's why like this design got more shredded.
Yeah, I mean, I think so. It was also the ThickSat one just seemed to be more energetic in general when deploying, and it also had like this resulted in like a sudden stop when it emptied. That could have also caused issues. Like this new one, it doesn't seem to have quite the same elasticity as ThickSat, so it's a much more gentler deployment.
Yeah. Any questions from our folks online? Anything else? Okay. Otherwise, yeah, thanks everybody for joining. We'll be back here in 2 weeks, probably with another ProSat seminar from Devin. But yeah, thanks. Thank you for the great presentation. Yeah, I agree. We put it perfectly. Gustavo, well, that's a great kind of history and evolution of the timeline. It's really interesting to see that kind of progression that went on there. So, but yeah, but thank you very much for presenting, and anybody else joining online, thank you. With that, we'll see you in 2 weeks.